You think you know where a tree comes from. Of course you do. You've seen it thousands of times. A tiny seed falls to the ground. Some water, some sunlight. Then a tree sprouts up. Simple. Obvious. So obvious that no one bothers to question it again. But some obvious things are spectacularly wrong. Take a look at an oak tree that weighs a ton, standing tall, solid, full of dense matter, and ask yourself, where does all this matter come from? From the soil. Sounds reasonable. But how much does the soil weigh? How much does the tree weigh? And why doesn't the soil sink down as the tree grows? From water. Could you fill a barrel with water and have it turn into a tree trunk weighing hundreds of kilograms? This is the moment when the things you believe are true start to wobble, forcing you to re-examine your entire intuition. Because that seemingly childish question, where does a tree get its mass from, actually touches on one of the deepest truths about the world. A truth so beautiful, it's almost unbelievable. And let's tear open that familiar illusion together. Come on. We're about to see the tree with completely new eyes. Let me tell you a story that should have shaken every science classroom for hundreds of years. But for some strange reason, it got reduced to a tiny footnote in textbooks. In the early 1600s, there was a guy named John Baptist van Helmont, the kind of person who, if you invited him to a party, would sit in a corner, muttering things like, that's odd. How exactly does this tree grow? And instead of pretending to be satisfied with the usual answers, like the rest of humanity, he decided to test it, experiment, measure properly. That's why I like this guy. He didn't trust intuition. He trusted numbers. Helmont took a small willow tree, weighing exactly 5 pounds, and planted it in a tub of soil that had been dried and precisely weighed at 200 pounds. No more, no less. For the next 5 years, he did only one thing, watered it. No added soil, no fertilizer, no secretly mixing in anything else. 5 years passed, and you know how trees are. They don't care if you're conducting an experiment. They just keep growing. That willow tree ended up weighing 169 pounds, meaning it had gained 164 pounds of brand new matter. Okay, at this point you'd say, obviously it came from the soil. Great, Helmont thought so too. So he did what any real scientist would do. He dried the tub of soil and weighed it again. And guess how much soil was lost? Less under 2 ounces. 2 ounces of soil couldn't possibly turn into 164 pounds of tree. No physical miracle works that way. If someone told you their 2-ton car was made from 1 melted aluminum spoon, you'd call them crazy. Yet we believe an entire massive tree appeared from a bit of soil depleted by less than a cookie's worth. Helmont's experiment, simple enough that a child could do it, shattered the assumption the whole world had believed for thousands of years. Soil is not what creates a tree's mass. All right, so on to suspect number 2. Water. Sounds a bit more reasonable, right? You see roots sucking up water. The trunk is moist, leaves full of vapor. Easy, trees grow by drinking water. The only problem is, water can't do that. AO is basically 2 hydrogens and 1 oxygen. Hydrogen, sorry to say, is just about the lightest thing in the universe. If a tree were mostly made of hydrogen, you could lift an entire oak with 2 fingers. What about oxygen? The tree splits AO, uses the hydrogen for chemical processes, and the oxygen, the slightly heavier part, it releases back into the air. That's exactly what you're breathing in. I know this sounds a little unfair. You expected water to contribute to the tree's mass, but it mostly contributes to the mass in your lungs. In short, water cannot be the source of a tree's mass, except for a tiny fraction related to the hydrogen in molecular structure. But hydrogen is far too light to account for hundreds of pounds of wood. Hypothesis number 3, minerals in the soil. This is why people always say you have to fertilize, use rich soil, but minerals only make up 1 to 2% of a tree's dry mass. Meaning if you burn a tree, the ash left behind basically the minerals, is roughly that proportion. You can't build a skyscraper from a pile of bricks that make up just 1% of the mass. No scientific theory allows that to happen. And this is the moment that should make you furrow your brow deeply. Soil isn't it. Water isn't it. Minerals aren't it either. Three hypotheses, once considered obvious, have now collapsed under the weight of numbers. So where did those 164 pounds come from? A tree heavier than you, me, and the table we're sitting at, and we can't explain what it's made of. Not soil, not water, not minerals. And if this makes you feel a little unsettled inside, good. That's a sign you're about to learn something truly important. So what else is left? If it's not soil, not water, not minerals, then what created those 164 pounds of brand new matter in Helmont's experiment? This is the point where I have to say the sentence that in my experience always makes the audience either burst out laughing, sit in stunned silence, or immediately suspect I've lost my mind. But I'll say it anyway, because it's true. Trees are made from air. Yes, it sounds absurd. It sounds like a joke from an eccentric professor trying to shock freshmen. But if you follow the logic, real logic, the kind not blocked by faulty intuition, you'll see there's no other answer that fits the data. Think of it this way. The air around you contains CO5, carbon dioxide, a molecule with one carbon atom in the middle and two oxygen atoms on the sides. When a tree eats CO5, it doesn't swallow all three atoms and store them in its trunk. It's picky. It keeps the carbon, and this carbon is heavy, truly heavy in the physical sense, while releasing the two oxygen atoms, the lighter but bulkier part, back for you to breathe. What does that mean? It means every time you stand under the cool shade of an oak tree and take a deep breath, you're inhaling the exact oxygen pieces that tree decided it didn't need. Imagine this. You and the tree are exchanging molecules, like two roommates sharing snacks, except the tree gives you oxygen, and you give back CO5. What a beautiful relationship. But here's what's important. The carbon the tree keeps is exactly what forms the trunk. Branches, leaves, bark, wood, everything you can touch. That carbon once floated invisibly in the air, completely outside your attention. And now it's standing right in front of you as a giant, silent, solid, multi-ton organism. You can lean against it. You can carve it into a table. You can burn it for heat. If you're sitting at a wooden table right now, it's basically old air, just carbon that was separated from oxygen and neatly rearranged into solid form. You couldn't see the carbon when it was gas, but you see it clearly now that it's wood. That doesn't mean the carbon disappeared or appeared from nowhere. It just changed form. And this is the moment your old intuition, soil makes trees, completely collapses, and a new intuition begins to form. Air has mass, and a lot of it we just don't notice because we've lived immersed in it our whole lives. It's light compared to water, light compared to rock, but it's not weightless, it's not empty. 1 cubic meter of air weighs about 1.2 kilograms, and the CO hardar in it, even though it makes up only about 0.04%, comma, is an endless source of carbon for trees to use. The more you think about it, the more you realize it's too simple to have been overlooked. The tree stands there, spreads its leaves, and pulls CO hardars in as if it's quietly gathering bits of matter from the sky. Then it uses sunlight, something we still think of as brightness or warmth, to break apart CO hardars, keep the carbon, release the oxygen, and start building its own body from those carbon atoms. No magic, no mystery, just physics and chemistry working beautifully. And you know, when I say trees are made from air, it's not a metaphor, not some vague philosophical idea about universal connection. It's a measurable, verifiable, repeatable physical truth you can test in a lab. The tree in front of you is air reorganized, rearranged, and bonded together by the energy of the sun, from something invisible to something solid, from a lightweight molecule drifting in the wind to an object you can hug, lean on, or even cut down. But I don't want you to stop at amazement, because the next question, and my favorite one, is how does air become wood? How does a fragile CO molecule floating in the wind turn into a heavy kitchen table or a wooden beam in your house? To understand the strange story that trees are truly made from air, we have to start with what seems simplest but is most easily misunderstood. Air is real matter. I know it sounds obvious, but trust me, most people live their entire lives without truly realizing this in the physical sense. We don't see air. We walk through it every day. And the human brain, which is pretty lazy about these things, quickly slaps the label empty on the entire sky around it. But nature doesn't care about those convenient labels. Air is made of molecules, constantly in motion, with mass, with density, and most importantly, it can exert force. If you've ever inflated a ball, you've seen it. When the ball is flat, you squeeze it like a sponge. When you pump air in, it swells, hardens, and if you pump hard enough, it bursts. Simple question. If air is nothing, then what's pushing the ball to expand? Nothing can split rubber. Another example, car tires. You pump more air in, and suddenly you can lift the car weighing over a ton with that invisible stuff. There's no magic here, just an enormous number of gas molecules compressed together, creating pressure. That pressure lifts the car. If air were truly empty, you couldn't do any of that. And now for the part most people don't know. The column of atmosphere above every square meter of ground weighs about 10 tons. Yes, you're sitting under 10 tons of air right now. Your body has just evolved to balance that pressure from the inside, so you don't get crushed like a soda can. Once you accept that air has real mass, you can move on to the most interesting part. CO4 is also real matter, and it's the floating carbon stock around you. In the atmospheric mix, CO4 makes up only 0.04%, which sounds negligible. But if you multiply that tiny number by the gigantic volume of air covering the entire planet, you realize it's actually a massive raw material reserve. More importantly, the carbon in CO is heavier than the nitrogen and oxygen in air. If you inflated one ball completely with CO and another with normal air, the CO ball would weigh more. That means the carbon in CO is real matter with real mass, and that's exactly the atom the tree wants. The tree takes a CO molecule, splits off the carbon to build wood, and returns the 2 oxygen atoms to the air. In other words, you're breathing the tree's leftovers. But the carbon, the part the tree keeps, is the fundamental building block of wood structure. This seems hard to believe, only because we don't see CO floating around us. If the carbon in the air sparkled like gold dust, you wouldn't find it strange at all that trees grow from it. But because carbon is invisible, your brain automatically dismisses it. Intuition says, not seen equals sign, not there. Physics says not seen equals sign, still has mass. Look at a big tree. An oak can weigh tons. It's hard to believe most of that matter was once scattered around you as sparse CO molecules. But trees don't need a lot at once. They just need time. Year after year, leaves continuously absorb CO, retain carbon, and stack that carbon into cellulose, lignin, and everything that makes wood. Imagine picking up stray coins every day. One coin means nothing, but if you pick them up for 50 years, you have a fortune. Trees do that with carbon, and this brings us to the real turning point. For the carbon in CO to become wood, the tree must split CO, keep the carbon, discard the oxygen, and then build the carbon into complex molecular networks. This isn't biological magic. It's a sophisticated physical-chemical process. And to do that, the tree needs a tool. It can't make itself sunlight. The light you think of as just brightness or warmth is actually electromagnetic energy, carrying enough power to break apart CO hard molecules, something you couldn't snap with your hands, a hammer, or your teeth. That light energy is contained in every photon. When you realize that most of a tree's mass comes from CO hard in the air, the logical next question isn't why, but how. And this is where nature shows off its elegance, to the point of almost being humorous. A leaf has no mouth, no pipes, no lungs to breathe like you do, and it certainly has no heart to pump gas. Yet every leaf can take in trillions upon trillions of CO hard molecules every day. The secret lies in a system so tiny, you could go your whole life without knowing it exists. Stomata. Each stoma is only about 1080 micrometers wide, meaning you could fit hundreds of them on the head of a human hair. A single leaf of a red maple can have up to 300,000 stomata per square centimeter. Leaves of many ancient fern species have fewer, around 10,000, 20,000. It depends on the evolutionary environment, light intensity, and photosynthetic needs of each species. Stomata look like tiny doors, formed by two bean-shaped cells called guard cells. When the guard cells take in water, they swell and the slit opens. When they lose water, the slit closes. This is an elegant mechanism that requires no brain, just osmotic pressure, something biology exploits with incredible finesse. But stomata aren't what pulls CO hard in. They just open the door. The rest is handled by pure physics. Diffusion. The air around you contains about 420 ppm CO hard. That means in every million air molecules, 420 are CO hard. It sounds small, but in every breath you take there are about 1020 gas molecules. So even 420 ppm is an enormous number. Now look at what happens inside the leaf, where CO hard is constantly being used for photosynthesis. The internal CO hard concentration drops to just 100, 200 ppm. When the stomata open, this concentration difference causes CO hard to move in on its own, exactly like the smell of coffee spreading from the kitchen without anyone stirring it. This is diffusion, the principle first described experimentally in 1827 by Scottish experimenter Robert Brown, and mathematically explained in 1905 by a young student named Albert Einstein, who showed that the random motion of molecules can be fully described by probability. And it's that probabilistic mechanism that's supplying carbon to every forest on the planet. A white oak leaf can absorb about 5-10 micromoles of CO hard per square meter per second under strong sunlight. In terms of molecules, that's roughly 3 per second, turned per CO hard molecules per second through a tiny area the size of a few sheets of paper. Imagine the whole tree, imagine the entire forest, and imagine the absolute silence in which every CO hard molecule is making an invisible journey through the tiny doors of the leaves. Trees also adjust stoma size according to temperature, humidity, and light. For example, many CO hard plants like wheat open their stomata most strongly in the morning when light is sufficient but temperature isn't too high yet. In contrast, cane plants like cacti open their stomata at night to minimize water loss, a brilliant strategy for desert environments. A single stoma can open or close in 30-60 minutes, but when millions coordinate, the adjustment becomes so smooth it almost resembles intentional behavior. But the most fascinating part happens after CO hard has passed through the stomata. Beneath the leaf surface is a vast network of air spaces interspersed between cells called mesophyll. The mesophyll space takes up to 40% of the leaf's volume. Like wide corridors, in a tiny chemical factory. CO diffuses through this network, moving between cells like commuters in a crowded train station until it reaches the chloroplasts. Those light factories, about 5 micrometers in diameter, that contain the entire production power of photosynthesis. I want you to imagine this: a leaf lying still under the sun, not shaking, not glowing, making no sound. But beneath that thin tissue, billions of CO molecules are drifting in, billions of ether molecules are drifting out, and billions of chemical reactions are happening every second. If your eyes could see molecules, the leaf would light up like a city at night, with endless streams of traffic. And the loveliest thing here is the tree doesn't seek CO. It just creates the situation where CO comes to it on its own, like placing a bowl of water in the desert and waiting for animals to drink. Except here it's an eternal physical law working for the leaf. When you touch a leaf, you're touching the outer shell of a system that operates on diffusion, regulated by water, opened by God's cells, and perfected by evolution over more than 400 million years, ever since the first plants left the ocean in the Silurian period. And all of this, every stoma, every CO molecule, every concentration gradient, is just the first step. When CO has slipped into the leaf through those tiny stomata, its journey hasn't really begun yet. Carbon is there, sure, but it's still locked tight in an extremely stable CO molecule. The tree needs a powerful enough energy source to break this molecule apart, and that energy source is light. The problem is most people hear light and think of something simple: brightness, color, the thing that lets us see objects. But in the language of physics, light is electromagnetic radiation, oscillations in the electromagnetic field, traveling at 300,000 kilometers per s. And most importantly, light isn't a smooth stream of energy. It's packaged into discrete packets of energy called photons. Imagine photons as ultra-tiny quantum bullets fired from the sun. Each photon carries a specific amount of energy depending on its wavelength. Blue light photons carry more energy than red ones. The tree, though it doesn't think, has evolved to use precisely the band of light with the most suitable energy, thanks to chlorophyll molecules in the chloroplasts, molecular antennas, perfectly tuned over hundreds of millions of years. When a photon hits chlorophyll, it doesn't heat the leaf or make it glow. Instead, it does something ordinary chemistry struggles to achieve. It knocks an electron to a higher energy level. That's the crucial moment. In just a few billionths of a second, that electron now carries energy from a star 150 million kilometers away. That electron is immediately swept into a chain of proteins called the electron transport chain, a system so sophisticated that if you scaled it up to washing machine size, it would probably look more complex than any human industrial assembly line. The ultimate goal of this chain is to produce two forms of chemical energy, ATP and NADPH. This is the energy the tree will use to break CO. And if you're wondering why it takes so many steps, the answer is the C equals sign. O bonds in CO are extremely strong. Under normal conditions, you couldn't separate carbon from oxygen without temperatures over 2000 degrees Celsius. But the tree can't turn itself into a furnace. It needs strong, yet delicate energy, and photons are the perfect candidate. Sunlight reaching Earth provides about 1,000 watts ennued the summer, but the tree absorbs only a small fraction of that, enough to excite electrons without destroying the leaf structure. This is a beautiful balance. Photons carry just enough energy to start chemical reactions, but not so much that they damage the fragile leaf. And what's even more astonishing, a single photon can excite one electron, and that electron can trigger an entire chain of reactions, producing thousands of energy molecules. One tiny photon leads to a cascade of large effects, from electron to ATP, from ATP to Cl taut. This makes light structural energy, energy that can change molecular structure. It doesn't just illuminate the leaf, it builds the leaf from the inside. When you look at a leaf in sunlight, you see calm appearance, but at the molecular scale, it's a quantum factory running non-stop. Every second, millions of photons are absorbed, millions of electrons are excited, and that energy is carefully collected for the next step, splitting CO2. Without photons, carbon would stay forever in the sky, and every tree on Earth couldn't grow beyond a sprout. No photons, no wood, no wood, no forests, no oxygen for you to breathe. That's why light isn't an accessory factor in photosynthesis. It's the core power source, the only quantum hammer delicate enough to break Cl taut. You can imagine this moment as a gentle but precise kick. The photon vanishes completely. Its energy no longer exists as light and is fully transferred to the electron, boosting it to a higher energy level. This is called the excited state. It sounds poetic, but it really just means the electron is now like a kid who's been stuffed full of sugar. It can't sit still. The electron can't stay excited forever because nature prefers stability. So it has to go somewhere to release the energy it just gained. And the tree, in an incredibly clever way, has pre-installed a pathway for the electron to run through, a molecular track called the electron transport chain. You can picture the electron transport chain as a series of connected train stations made of proteins lined up on the thylakoid membrane inside the chloroplast. The electron jumps from station to station, and with each jump, it loses a bit of energy, but the energy doesn't disappear. It's collected and used to pump protons across the membrane, creating an electrochemical gradient, and that gradient is the energy source for synthesizing ATP, the universal energy currency of every organism on Earth. If you've ever seen water flowing through a hydroelectric dam, you get the idea. The photon is like rain upstream, the electron is like water lifted high, and the electron transport chain is like the turbine system harvesting energy as the water flows down. Nothing is wasted. Every bit of energy the photon brought is converted into usable chemical energy. Inside a chloroplast, there are thousands of chlorophyll molecules, and each can absorb photons continuously while light hits the leaf. This means countless electrons are being excited and rushing into the electron transport chain at the same time, creating a massive but utterly silent flow of energy. At the molecular scale, the light reaction is a chaotic yet highly organized migration, where electrons are guided from high to low energy levels along a path optimized by evolution over hundreds of millions of years. During that journey, the electron gradually loses energy, and that energy is used to pump protons from one side of the thylakoid membrane to the lumen, building an extremely strong proton concentration difference. This difference is like a tightly compressed water balloon. The protons want to flow back, but there's only one door for them, an enzyme shaped like a turbine called ATP synthase. When protons flow through ATP synthase, they spin the molecular rotor, literally spin, and that motion attaches a phosphate group to ADP to form ATP. If anything deserves to be called one of nature's most magnificent inventions, it's ATP synthase, a molecular generator, a few nanometers in size, that powers all of life. The beautiful thing is, it all starts with one photon. Photon excites electron. Electron runs through the transport chain. Transport chain creates proton gradient. Proton gradient runs through ATP synthase. ATP is produced, and ATP is the energy the tree uses to split CO4s, build glucose, assemble cellulose, and ultimately create the wood you can turn into a table, a floor, or a guitar. Think about this image for a second. You're standing under a tree canopy where the cool shade feels pleasant. But in the leaves above your head, millions of electrons per second are jumping energy levels. Millions of protons are flowing through molecular turbines, and millions of ATP molecules are being made, all in silence. No machinery, no pistons, no wires, no metal turbines, just electrons, protons, and sunlight from the sun. The light reaction is where light gets packaged into chemical energy, energy the tree can use to break tough molecules, like CO part. Without the light reaction, the tree wouldn't produce ATP, couldn't split CO part, couldn't make sugar, and all life that depends on photosynthesis would collapse. In other words, every forest, every field, every breathing creature on this planet depends on the dance of electrons when photons hit chlorophyll. And this is my favorite part. The light reaction doesn't just turn light into energy. It turns the presence of a star into the ability to build solid matter. Sunlight, after a 150 million km journey, is finally absorbed and converted into ATP. And ATP is the energy brick used to turn air into wood. And now, when the electrons have finished their journey through the transport chain and created the proton gradient, we finally reach the most important product of the light reaction, ATP, or adenosine triphosphate, the thing biologists often call the energy currency of life. And I really love that name because it's not just biochemically accurate, it's incredibly intuitive. ATP is the money every organism on Earth uses to pay for energy-requiring work. Want to break CO apart? Pay with ATP. Want to build a glucose molecule? Pay with ATP. Want to polymerize millions of sugar units into cellulose to make wood? Once again, pay with ATP. Trees, bacteria, humans, mice, elephants, blue whales, all use the exact same currency. No exceptions. The beautiful thing is, sunlight has been exchanged into ATP through the light reaction. In other words, photons from the sun have been converted by the tree into a tangible form of chemical energy. Of course, tangible in the molecular sense. Now, to understand ATP's role, imagine you're building a house. The raw materials, bricks, cement, steel, don't assemble themselves into a house. You have to pay workers, pay for machinery, pay for supplies. No money. The house is just a useless pile of materials. For the tree, carbon from CO part and hydrogen from water are like building materials. But to connect them into larger structures, into sugars, then into cellulose, the tree has to pay with ATP. ATP is like stacking $1, $5, $10 bills in your wallet. Each ATP molecule carries a small but sufficient amount of energy to do a specific job. The tree needs millions of ATP molecules to make just 1 gram of wood. So when you hold a piece of wood in your hand, you're actually holding a block of solar energy that the tree spent over years. And the way ATP is produced in the chloroplast really deserves to be one of the most beautiful moments in natural physics chemistry. Remember the proton gradient, the electrons created earlier. It's like an energy reservoir compressed on one side of the thylakoid membrane. Protons want to flow back because nature hates imbalance, but there's only one path for them, the enzyme ATP synthase. And ATP synthase is a true molecular machine. It rotates. Yes, rotates in the literal mechanical sense. As protons flow through ATP synthase, that flow spins the molecular rotor. As it spins, it attaches a phosphate group to ATP to create ATP. If you like a visual, imagine each ATP synthase molecule as a tiny wind turbine, where wind is replaced by protons and electricity is replaced by ATP. The sophistication of this natural design makes many biochemists joke that ATP synthase looks like something a genius drunk engineer would draw, ridiculously complex looking, yet it works perfectly. Once ATP is produced, it immediately becomes the currency the tree uses for the next step, breaking CO fast, something that would be nearly impossible at room temperature without ATP. Remember that CO fast is an extremely stable molecule. It has no reason to split on its own, just like a worker has no reason to work if you don't pay them. ATP is that paycheck. The tree uses ATP's energy to pay for the CO fast splitting reaction in the Calvin cycle. The Calvin cycle works like an assembly plant. It takes CO fast as raw material, uses ATP for energy, and NADPH for the necessary electrons. The end result of this cycle is G3P, a simple molecule the tree can turn into glucose, then cellulose and lignin. But the key point here is, without ATP, the Calvin cycle stalls. No ATP, no carbon gets split, no split carbon, no sugar, no wood. And that's why ATP isn't just energy currency as a metaphor. It's real currency in the chemical sense. If ATP runs out, the tree's entire molecular economy collapses. And you can extend this to the whole biosphere of Earth. Every living thing, from a 100-meter eucalyptus to a bacterium in your gut, uses ATP to live. When you run, your leg muscles consume about 1 billion ATP per second. When you sleep, your body still consumes ATP. And all that ATP is constantly regenerated, millions of times a day. The truth is, if your body stopped producing ATP for just 2 minutes, you'd die. Trees are no different. Photosynthesis is its ATP production system, and ATP is the currency it uses to turn air into tree trunks. One more interesting thing, ATP in trees is completely renewed every few seconds. It doesn't store energy long-term like fat or starch. It exists only briefly, produced and consumed almost instantly. That means light energy must be absorbed continuously to maintain the ATP flow. That's also why trees can't photosynthesize at night. No photons, no excited electrons, no ATP. So if you want to picture a tree in true physical terms, imagine a machine that uses sunlight to print out ATP bills. Then it uses those bills to buy materials, hire molecular construction crews, and build layer after layer of carbon to erect a complete tree. That's the energy economy of life. Photon, electron, ATP, sugar, wood. The process of creating ATP and NADPH in the light reaction is just the beginning. Now we move to the hardest, most expensive, and strangest step of all photosynthesis, breaking the CO2 molecule. This is the step I always joke that if anything deserves to be called real magic, this is it. Because CO2 is an incredibly stable molecule. It's the end product of combustion, meaning carbon has fallen to the lowest energy state it can reach when combined with oxygen. That's why burning wood, gasoline, or any organic material releases heat. Energy is released as carbon moves from a high energy state to a low one. But that also means to separate carbon from CO2, the tree has to do the opposite. Push the molecule up to a higher energy state, a reaction nature really doesn't want to do at all. So how does the tree pull off this reluctant feat? Not with heat, not with pressure, not with mechanical force. Instead, it uses an extremely sophisticated molecular machine made of ATP, NADPH, and the enzyme ribisco, a trio that has been evolving for over 3.5 billion years. Ribisco isn't just the enzyme that performs the first step in carbon fixation. It's also the most abundant protein on Earth. If you weighed all the ribisco in every plant, every alga, every cyanobacterium, its mass exceeds the total mass of all animals on the planet. And it's no accident. Rubisco does the single most important job that life depends on. It captures individual coal-based molecules and pulls carbon into the organic world. Specifically, Rubisco attaches coal-base to a 5-carbon molecule called RuBp. This is the first step in the Calvin cycle, deciphered by Melvin Calvin in the 1950s, earning him the Nobel Prize in Chemistry in 1961. But don't let the word cycle make you think everything runs smoothly. The reaction between Cl coal-base and RuBp is an extremely difficult chemical reaction to occur. Rubisco has to position the Cl coal-base molecule, hold it long enough in the exact right spot, and break the stable structure of Cl coal-base so the carbon can attach to RuBp. This is where ATP and NADPH step in. You can think of ATP as the energy paying the workers and NADPH as the electron source to build the new structure. Rubisco can't work without them, just like you can't build a house without cash and without electricians. When Cl coal-base is finally attached to RuBp, the new molecule splits into two 3-PGA molecules. This is a crucial milestone. For the first time, carbon from the air is fixed into organic form. Physically, this is the moment air begins to become matter. From 3-PGA, the tree uses ATP and NADPH to turn them into G3P, a versatile 3-carbon molecule that plants can transform in any direction into glucose, fructose, sucrose for transport, or cellulose to build wood. Some G3P is withdrawn from the cycle to build matter. The rest is recycled back into RuBp, keeping the Calvin cycle turning. That's why it's called a cycle. It repeats continuously. Now imagine the scale of this process. In a leaf the size of your palm, billions of Cl coal-base molecules are captured by Rubisco every second. In a forest spanning hundreds of hectares, this process happens at an unimaginable rate. If you gathered all the carbon fixed by the Amazon rainforest in 24 hours, it would equal the mass of millions of truckloads. And it all starts from tiny molecular reactions happening in absolute silence on every leaf. Atmospheric Cl coal-base has no reason to become wood. It only does so because the tree pays energy, paid with ATP. The tree spends ATP to perform a reaction that goes against nature. And because of that, carbon leaves its gaseous form and enters the organic world. You can picture the tree as a construction company. Carbon is the raw material. ATP is the budget. Rubisco is the main workforce. NADPH is the electrical engineering team. The Calvin cycle is the production line. G3P is the first product, a molecular brick that can be assembled into anything else. And from these G3P bricks, the tree builds glucose, then polymerizes it into cellulose and lignin, the final structures that make up wood. The beautiful thing is, all the carbon in the tree trunk, every growth ring, every grain of wood, every leaf once was Cl coal-base in the sky. That carbon was pulled down by Rubisco, paid for by ATP to be retained, and supplied with electrons by NADPH to build organic molecules. And if you burn wood, the energy released is exactly the solar photon energy the tree locked away in chemical bonds years ago. Breaking Cl coal-base is the most important step in the journey from gas to tree. This is the boundary moment between air and living matter. If this step stops for lack of ATP, NADPH, light, or Rubisco, life on Earth stops immediately. If breaking CO hard is the moment the enzyme pulls carbon out of the sky, then making glucose is the moment that carbon becomes stuff, something you can weigh, touch, burn, or eat. This is where air begins to solidify into matter, atom by atom. G3P is a 3-carbon molecule, so to make glucose, a 6-carbon molecule, the tree simply combines 2 G3P molecules and refines them with a few more chemical steps, adding hydrogen and oxygen from water, energy from ATP, and adjusting bonds to create a stable structure. The overall formula for glucose is C-havno, or HAV, or carbon chain forming the backbone, supplemented with hydrogen and oxygen to create a molecule that is not only energy-rich, but can also serve as the foundation for building larger molecules. The most astonishing thing is all the carbon in glucose comes from the air. Hydrogen comes from water. Oxygen comes from water, or is rearranged. But the backbone, literally in the physical sense, is carbon from the sky. So when you say trees grow from air, it's not metaphorical. It's molecular fact. Every sugar granule, every starch molecule, every piece of wood that ever existed began with linking carbon atoms captured from CO-HAV into a glucose molecule. Glucose is the basic building block of life on Earth. It's the first truly shaped organic matter with significant mass, stored energy, and the ability to be transformed into more complex substances. That's why I like calling glucose the first brick in the tree's construction project. If you look at a tree trunk, you're looking at trillions upon trillions of transformed, linked, polymerized glucose bricks that make up the wood. But before glucose becomes cellulose or lignin, it's just a beautiful, chemically flexible, 6-carbon molecule, ready to become whatever the tree needs. To understand how crucial glucose is, imagine building a skyscraper. You could use red bricks, wood, steel, cement, glass. But if you break down every material to its most basic level, you'll find characteristic small blocks, repeating basic modules. In the tree, glucose is that module. It's simple enough to produce quickly, flexible enough to transform, and energy-rich enough to serve as fuel. And the tree has optimized the glucose production process to an astonishing speed. On a sunny day, 1 square meter of leaf canopy can produce 10-20 grams of glucose in just a few hours, all from CO-HAV that your eyes can't see. Pause for a moment and think the first glucose molecule created from air is the moment the invisible world shifts to the visible world. From lightweight, shapeless, untouchable gas molecules, the tree creates a solid molecule that can be stored, transported, and used. This is the first time atmospheric carbon is incarnated into something that can become trunk, roots, leaves, fruit, seeds, wood, and ultimately even a guitar hanging in your room. And what makes this process even more fascinating is how the tree handles glucose. It doesn't keep glucose like sugar in your coffee cup. It uses glucose as a versatile molecule, cutting it, pairing it, changing its structure, rotating bond angles, and creating a whole series of complex molecular forms. Some glucose is converted to sucrose, the sugar the tree uses to transport energy throughout its body, equivalent to molecular logistics. Some is converted to starch, the energy reserve for nights or winter. And most importantly, glucose is polymerized into cellulose, long polysaccharides, thousands of units long, forming the main structure of the tree trunk. You could call cellulose nature's biological concrete. It makes up about 40–50% of the dry mass of wood. And cellulose, despite having a very different structure from glucose, still begins with those very glucose bricks. Another portion of glucose enters the pathway to create lignin, which makes wood hard, load-bearing, and water-resistant. If cellulose is the frame, lignin is the cement holding the frame together. But all of it, cellulose, lignin, starch, sucrose, shares one thing in common. They are built from glucose, and glucose is built from atmospheric carbon. Think about it carefully. This is truly extraordinary. In a world where all matter originates from something tangible, soil, rock, water, the tree builds its body mostly from something invisible, and glucose is the molecule that marks that transformation moment. The light reaction and Calvin cycle don't create the tree trunk instantly. But once glucose appears, everything else becomes possible. And here's another interesting thing I bet you've never thought about. Glucose is made in the leaves, but can become any part of the tree. It can travel down to the roots, up to the branches, flow through xylem and phloem, or be pulled out of the transport stream to become new cells. As if the tree takes this first brick and says, all right, I'll use this brick to build my world. And when you look at a 200-year-old ancient tree, you're looking at trillions upon trillions of such bricks, fitted precisely and more tightly than any building humans have ever constructed. But it all began with just one thing: atmospheric carbon linked into glucose. That's the moment air truly becomes matter. Once glucose has been created, the first carbon brick extracted from the air, the tree immediately moves on to a much larger task: building real structure. No longer just tiny sugar molecules floating in cells. This is when they must be turned into something that can stand against wind, lift the canopy to the sky, and last for decades or centuries. And to do that, the tree must turn glucose into cellulose, the main structural material of wood and the most abundant organic compound on the planet. Cellulose isn't a single molecule. It's an endless polymer chain created by linking thousands of glucose molecules together in a very specific way. The beta-monomer 4-glucosidic bond. The name sounds complicated, but the physical meaning is very simple. If glucose is individual links, then cellulose is a long, straight, strong chain. A single glucose molecule is weak. It dissolves in water, easily broken down by enzymes. But when thousands of glucose molecules are linked correctly, the tree creates a polymer chain with tensile strength greater than steel by weight. And this is exactly why glucose must exist. The tree can't build its body directly from CO5. It has to create a simple brick, then use countless of those bricks to build its own universe's framework. Imagine you have a box of Lego with thousands of identical pieces. One Lego piece is nothing special, but assemble them according to the rules, and you can create walls, columns, bridges, towers. The tree does the same at the molecular level. The enzyme cellulose synthase is that Lego assembly machine located in the plant cell membrane. Cellulose synthase pulls in individual glucose molecules, links them into straight chains, then pushes the growing cellulose fiber out to assemble into the cell wall. You can picture this as a molecular 3D printer working 24/7, never stopping, never making noise, never vibrating, consuming nothing but energy and a glucose supply. When hundreds or thousands of cellulose chains are produced in parallel, they automatically arrange into bundles called microfibrils. Those microfibrils twist together into macrofibrils, larger, stronger fibers that form the load-bearing framework of the cell wall. And billions of such cell walls join to form wood tissue. The end result, a tree trunk that can reach 30 meters tall, weighs several tons, yet still stand firm against storms. This is truly impressive when you remember that cellulose is held together mainly by hydrogen bonds, the kind of bond you break just by stirring water. But when millions of hydrogen bonds work together, their combined strength creates a material so hard you need an axe or saw to cut it. The tree invented an ultra-durable composite material from weak bonds simply by arranging them in order. That's the most beautiful physics lesson. Structure matters more than material, and cellulose demonstrates this perfectly. But cellulose isn't only in wood, it's in leaves, making them sturdy enough to capture light. It's in roots, helping them penetrate soil without being crushed. It's in fruit, in bark, in every plant cell. If you chew raw vegetables and feel the crunch, that's cellulose. If you write on paper, you're writing on cellulose. If you wear cotton clothes, you're wearing pure cellulose. The tree has used cellulose as the foundational material for every important function. What's interesting is that cellulose doesn't dissolve in water, an essential property. Since glucose dissolves in water, but cellulose doesn't, the tree can create a durable skeleton that isn't destroyed by rain or wind. This is like building a house from bricks instead of sugar. And just like bricks, cellulose is only strong when placed in the right structure. A single cellulose molecule can't support anything, but thousands of cellulose fibers, interwoven in multiple directions, form the secondary cell wall, the main load-bearing layer of wood. If you scaled it up to human size, this structure would look like a three-dimensional scaffold made of steel cables. Each individual fiber is weak, but together they're astonishingly strong. The most amazing thing is, all cellulose starts from glucose, and glucose is produced from CO2. You hold a piece of wood in your hand, and almost its entire mass is carbon that once floated in the air. You tap on a wooden table, and that thunk-thunk is the sound of air polymerized into solid matter. You're touching old air. But cellulose doesn't work alone. No matter how strong, cellulose is still a straight, flexible polymer. For the tree to stand tall, bear its own weight, and withstand weather, it needs a second material to fill the gaps between cellulose fibers, lock them in place, and turn them into real wood cells. Lignin. If cellulose is the steel frame, then lignin is the cement. If cellulose is the cables, lignin is the asphalt coating them. Lignin makes wood hard, waterproof, and resistant to decay. But cellulose is the first stage that turns atmospheric carbon into solid material. That's the step where the tree begins to erect the walls of its body. And this is when the second character of the wood world steps onto the stage, lignin. If cellulose is long, straight, flexible, yet strong cables, then lignin is the hard, rigid material that fills every gap between the cellulose fibers and locks the entire structure in place. Without lignin, a tree would be nothing more than a soft bundle of cellulose, like wet tissue paper. But with lignin, the tree becomes a pillar that can stand for decades, even centuries. This is the moment wood is truly created. Lignin is a complex polymer built from phenolic units, molecules with particularly stable carbon rings. If cellulose is a straight chain, lignin is a crooked branching network interwoven in every direction. This makes lignin extremely difficult to break down. That's why wood doesn't dissolve in water, doesn't soften when heated, and isn't easily attacked by bacteria. In fact, only a few groups of organisms on Earth can degrade lignin: white rot fungi, some rare bacteria, and time. That explains why wood lasts so long, because it's almost resistant to everything. When cellulose forms the aligned framework, lignin is synthesized in the secondary cell wall to fill the gaps between the cellulose fibers, as if someone poured molecular cement into the spaces between bundles of cables. The result is a natural composite material, hard yet flexible, durable yet lightweight. If you take a piece of wood and bend it, the force you're resisting is exactly the tension in the cellulose fibers and the compression in the lignin, a perfect molecular interplay. What's astonishing is that this entire structure, cellulose and lignin, is built from carbon that came from CO2. Thinking about it still gives me chills. The carbon you're looking at, touching, resting your hand on, all of it once floated invisibly in the atmosphere, like breath. And lignin is the step that turns those atoms into solid matter capable of defying gravity. If cellulose is like the rebar in concrete, then lignin is the concrete itself surrounding it, holding everything stable. But there's a crucial difference. Concrete is mainly good at compression, while lignin allows wood to handle both compression and bending, letting the tree sway in the wind without breaking. This is a genius invention that nature came up with hundreds of millions of years before human engineers understood composite materials. Another reason lignin is so important is its water-repelling ability. Cellulose absorbs water quite readily, but lignin is hydrophobic. This creates a kind of molecular armor that prevents water from penetrating deep into the tree, protecting the sap transport system and preventing rot every time it rains. A tree trunk is actually a gigantic water pipeline, so if cellulose absorbed too much water, the structure would collapse. Lignin solves this by sealing the gaps, hardening the conduit walls, and ensuring water only travels where it's supposed to, through the xylem. You can see lignin's importance by looking at a young, still soft tree. There, cellulose is abundant, but lignin is scarce. The trunk bends easily and breaks with little effort. But as the tree matures, lignin increases, cell walls thicken, and the entire tree becomes rigid, enough to build houses, bridges, or withstand storms. And the most wonderful thing is, lignin isn't a simple repeating structure. It's a messy polymer, almost no two segments exactly alike. That very messiness makes lignin so hard to break down. In the molecular world, the more regular something is, the easier it is to degrade. The more chaotic, the harder it is to decode. Lignin chose the chaotic path, and because of that, wood became one of the most durable natural materials. To illustrate lignin's role, imagine a bundle of plastic straws. You can bend the whole bundle, twist it, play with it. But if you pour epoxy glue between the straws and let it harden, you get a solid rod. That's exactly what lignin is. Nature's epoxy glue. It binds, reinforces, and creates overall hardness. And don't forget, the carbon in lignin is still carbon from the air. The phenolic rings in lignin, the things that give wood its brown color, hardness, and rot resistance, all began from glucose, and glucose began from CO-thiols. It took millions of years of evolution for plants to develop lignin. About 400 million years ago, in the Devonian period, lignin began to appear widely, and it was lignin itself that allowed trees to grow tens of meters tall. Before lignin, plants could only grow low because they lacked the rigidity to stand upright. After lignin, explosion of tall forests, climate change, formation of coal. Coal is mostly compressed lignin and cellulose over millions of years. Understanding lignin means understanding why our green planet has forests. And forests are gigantic machines that pull CO2 out of the atmosphere and lock carbon away in solid form. If cellulose is the fiber pulling carbon down from the sky, lignin is the clamp that locks it in place and keeps it there. When you tap your hand on a wooden table, you're hearing atmospheric carbon that's been held captive for decades or centuries. Wood isn't just material, it's fixed carbon. That also means every tree is a gigantic CO2 storage vault, and lignin is what makes that vault last long term. So now we have cellulose, long, straight polymer fibers, and lignin, the tough phenolic glue filling every gap. But there's still a deeper layer of meaning I want you to see, because if we stop at wood is cellulose plus lignin, we're only seeing the surface of the story. At the most fundamental level, wood isn't a polymer, isn't an organic compound, isn't a biological material. All those terms are just labels. In reality, wood and every solid thing you've ever touched is electromagnetic bonds. This is one of my favorite points in physics. When you peel away every layer of chemical, biological, even molecular explanation, you always end up with electromagnetic force. The force that pulls electrons toward the nucleus. Electromagnetic. The force that holds atoms together into molecules. Electromagnetic. The force that keeps molecules next to each other in solid material. Electromagnetic. The force that stops your hand from passing through the table. Electromagnetic. The material universe you live in is really a vast network of stable electromagnetic interactions, and wood is no exception. When you touch a tree trunk, you feel a solid surface. When you lean your back against it, you believe there's real matter supporting your body. But in truth, what's holding you up, resisting your weight, is the electromagnetic repulsion between the electrons in your atoms and the electrons in the wood. You've never truly touched wood. Your electrons simply come close to the wood's electrons. An electromagnetic force pushes them apart, creating the sensation of contact. This may sound strange, but once you grasp it, you start seeing the world the way physics sees it. Every solid object is a geometric arrangement of charges. So let's go back to wood. In cellulose, each glucose molecule links to the next via glycosidic bonds, a type of chemical bond formed when electrons from one atom are shared with electrons from another. That's electromagnetic. When cellulose chains run parallel, they link via hydrogen bonds, created by uneven charge distribution in the glucose molecule. Again, electromagnetic. Lignin, with its phenolic rings and oxygen-carbon bridges, is formed entirely by covalent bonds, meaning electrons are shared between atoms in a stable pattern. Electromagnetic once more. If you ask, so what is wood really? The most accurate physical answer is a stable network of electrons locked in a fixed geometric configuration. Wood isn't solid because of some special substance. Wood is solid because its electric field repels your intrusion. The difference between water and wood, between iron and feathers, isn't in some inner stuff, but in how their electrons are arranged and bound. In wood, long cellulose polymers with specific orientation are fixed by lignin into a sturdy three-dimensional network. In water, small molecules lack that fixation and only loosely connect, so they flow freely. In metals, electrons bond in a completely different way. They form a sea of free electrons that allows conductivity, but it's all still electromagnetic. This completely changes how you view matter. A tree isn't just wood. It's the shape that charges have chosen to achieve minimum energy stability under certain conditions. A wooden house is a monument of electromagnetic structure. A wooden guitar vibrates because of oscillations in that electromagnetic network, and the music you hear is really oscillations of electric fields in the air. Even the durability of wood comes from electromagnetism. When strong wind blows on a tree, cellulose fibers resist tension while lignin resists compression. But neither stretches or breaks immediately because electrons in the chemical bonds resist being pulled far from their stable configuration. You can call it material strength, but physics calls it electromagnetic bond energy. And what I love most about explaining wood this way is it brings us right back to the starting point. We said the carbon in wood comes from the air, but now you see a deeper layer. Carbon's ability to form stable electromagnetic networks is exactly why life exists in the material world. Carbon has 4 valence electrons. It can form countless different bonds, different bond angles, different molecular shapes. No other element has this incredible flexibility. With a few simple rules, carbon can create endless structures: sugars, cellulose, lignin, proteins, DNA, wood, leaves, you, me. All of them are intricate patterns of electromagnetic bonds. So when you look at a tree standing still on a hillside, you're looking at a gigantic electromagnetic architecture that began with photons, was assembled by enzymes, and perfected by electron bonds. And if you ask why wood exists as a solid instead of collapsing into powder or dissolving into liquid, the answer is very simple. The electromagnetic bonds in cellulose and lignin create the minimum potential energy in that configuration. Humans call it matter. Physics calls it stable electromagnetic field. I love how Einstein once described it. We call matter the stuff of the world, but really we're talking about the stability of fields. And this gives us a completely new way to look at a tree trunk. Wood isn't hard tree stuff. Wood is a 3D map of how electrons decided not to go anywhere else. It's stability. It's the shape of energy, when energy chooses to rest. And when you touch the tree, you're feeling the resistance of the electric field, an invisible but powerful force holding the carbon together. CO4 enters the leaf. Light excites electrons. ATP is produced. Carbon is broken from the gas molecule. Glucose appears. Cellulose and lignin build the wood, and everything solid around you is really just a stable electromagnetic structure of carbon. But we're still missing a bigger perspective, one I want you to feel, not just understand logically. Every tree is a material record of sunlight. It sounds poetic, but it's completely physics. A tree doesn't grow up the way humans grow up. It doesn't eat soil. It doesn't drink water to gain mass. Water is just a transport medium. Minerals are just helpers. Most of the tree trunk, almost all the carbon and structural energy, comes from two sources: atmospheric CO4 and sunlight. And if you put those two things side by side, what do you see? Something invisible, another invisible thing. But when the tree processes them, two invisible things become solid matter. This is what I want to emphasize. Trees are machines that turn light into matter. No metaphor, no exaggeration. Literally, trees take photons, packets of energy that travel 150 million kilometers from the sun's surface to a tiny leaf, and use those photons to break CO4, reassemble carbon into complex structures, and freeze solar energy into chemical bonds. Those bonds are the solid matter you can touch. Wood. The carbon in wood isn't just there. It's imprisoned in a stable state. Every time you burn a piece of wood, you're releasing sunlight energy the tree stored years ago. The spark that flares up is really ancient sunlight photons, returning to the world, back to free form, after being locked in chemical bonds for decades. You can accurately say that wood is frozen light, and a tree trunk is a real recording the history of the photons that entered it. Each growth ring is a record of each year's sunlight. Sunny year, wide ring, low sun or drought year, narrow ring. When you cut a tree open, you're reading the story of weather, of seasons, but deeper, you're reading the energy log of the nearest star. We, two-legged creatures wandering this planet, rarely think about it. We look at a tree and say, that's a plant, that's good wood, that's an old tree. But physics looks at the tree and says, here is where sunlight has stabilized into electromagnetic structure. Every grain of wood, every growth ring, every cell is crystallized light. And here's the strange thing that makes me smile. Every time I think about it, you can stand in the shade of a tree, enjoying the coolness, but really you're standing under a compressed pillar of sunlight. Wood isn't hard because of wood substance. Wood is hard because the electromagnetic bonds in cellulose and lignin are holding solar energy in a stable configuration. Solid matter is simply this, an energy configuration sitting at the bottom of a potential well, and light is what dug that well. Let me share an image I really love. Imagine each photon as a craftsman. It travels from the sun to the leaf, taps the electron lightly, hands over its tool, then vanishes. The electron uses that tool to build ATP. ATP pays Rubisco. Rubisco attaches Ki-O5 to Rubisky. The Calvin cycle produces Gi3P. Glucose appears. Glucose polymerizes into cellulose. Lignin fills the gaps. Cellulose and lignin assemble into wood tissue. Wood becomes the tree trunk. A single photon can be the spark that starts the formation of one wood cell. Billions of photons per second create thousands of cells. 1 year of sun makes one growth ring. 10 years of light make a wooden pillar. A century of light makes an ancient tree, and you can touch it, feel its solidity, lean against it, but you're leaning on ancient light that has taken physical form. Trees even store light in a special way. As the tree grows taller, it reaches for more photons. As the canopy spreads, the tree optimizes its light capture area. Trees have their shape not for beauty, but to catch as many photons as possible. Every canopy is a photon antenna. Every leaf is an electromagnetic energy receiver. Every trunk is a volt of frozen energy. If trees had consciousness, I think they'd say, I don't grow from soil, I grow from light. Everything in them, from sugars, starch, cellulose, lignin, to wood, is light in changed form. I want you to try looking at a forest with this mindset. Imagine each tree trunk as a pillar of condensed light, each canopy as an ancient solar panel, each branch as a place where photons decided to stop and become solid matter. A forest isn't just a biosphere, it's a 3D chart of how much sunlight fell on Earth over hundreds of years. When light is weak, trees stay short. When light is strong, trees grow tall. When conditions are favorable, trees expand. When conditions are harsh, trees contract. Forests are records of stellar energy, and when you look at a felled tree, you see the growth rings. That's not just weather history. It's the level of solar energy the tree received each year. Low sun year, small ring. Sunny year, large ring. Drought year, the tree conserved energy. Rainy year, the tree spent photons freely. All recorded in wood. Yes, wood is sunlight's diary. Nature doesn't just lock carbon into solid form. It locks in the accompanying energy story too. And this is what always makes the world feel beautifully simple to me. You live in a wooden house, meaning you live inside sunlight that was canned years ago. You light a campfire, meaning you're releasing ancient light. You strum a wooden guitar, meaning ancient photons are vibrating along the strings. It's hard not to feel the universe become a little more intimate when you realize this. A 1-ton tree, with its massive trunk, deep roots, lush branches and leaves, is made up of 990 kilograms from carbon, hydrogen, and oxygen that came from the atmosphere and water. Of that, carbon accounts for more than 50% of the dry mass. And this carbon comes almost entirely from CO4. That means the solid part of the tree, the stuff that makes the trunk, wood, leaves, bark, is carbon from the air. If you lift the wooden beam, you're lifting locked up air. It sounds surreal, but it's something chemistry and physics unanimously confirm. Let's do a simple calculation. A mature tree can contain about 500 kilograms of carbon. Carbon makes up 27% of the molecular mass of CO4. That means to create 500 kilograms of solid carbon, the tree had to absorb more than 1,850 kilograms of CO4 from the air. That's nearly 2 tons of gas, a number so large it surprises many people, because no one sees a tree eat air the way humans eat food. But trees do it continuously, molecule by molecule, billions of times a day. Many people react like this. But what about the soil? Roots absorb so much soil. Actually, roots don't eat soil. If you weigh the soil in a pot before and after a tree grows for a few years, the difference is very small, usually less than 1% of the tree's mass. Van Helmont's classic experiment proved this 400 years ago. He planted a 5-pound willow in 200 pounds of soil, watered it for 5 years. The tree gained 164 pounds, while the soil lost only 2 ounces. The minerals trees take from soil are very important, but they account for just 2% of total mass. That means when you see a towering brown trunk, you're not seeing soil rising up, you're seeing air rising up. The real mass of the tree mostly comes from carbon, hydrogen, and oxygen. Hydrogen and oxygen come from water, but the solid part, the part that makes wood, the part that makes the tree heavy, is carbon. And all of that carbon comes from the air. If this sounds paradoxical, it's because we're used to looking at trees from a biological perspective. Roots in soil, water in trunk, leaves in sky. Your eyes see roots in dirt, so your intuition decides this must be where the tree gets its mass. But eyes don't see molecules, and physics doesn't need visual observation. It demands data, and the data is very clear. Trees are CO habit-sucking machines that retain carbon. When you stand next to a big oak, you're standing next to a 500 kg carbon pillar pulled down from the atmosphere. And the beautiful thing is, trees don't do this just for themselves. The entire ecosystem depends on this process. Forests store carbon. Grasslands store carbon. Ocean algae store carbon. In fact, half of Earth's photosynthesis happens not on land, but in the ocean, done by tiny organisms you've never seen, but they suck CO habit terrifying rates. If all photosynthesis on Earth stopped for just a few weeks, atmospheric CO habit skyrocket, oxygen would plummet, and life would face catastrophe. No trees, no life as we know it. But back to the visible wooden tree in front of you. I want you to try an imagination exercise. Look at the trunk and disassemble the wood in your mind. You'll realize those carbon molecules once floated in the atmosphere as CO habits. Every time you touch a tree trunk, you're touching a piece of the atmosphere, solidified. If there's any magic here, it's this truth. Earth can't create organic matter from soil. Only light and air create it. Soil is just what keeps the trees standing upright, a storage place for minerals. Water just carries hydrogen and helps transport. But mass, real matter, comes from the atmosphere. This also leads to another shocking truth. Every animal, including you, is made from air. Air treat glucose, cellulose. Starch animals eat your body. The carbon in your brain cells was once CO5. The carbon in your bones once floated in the wind. Every carbon molecule in your heart was once air. So when we say trees come from air, it's not just a story about plants. It's the story of all life. Now compare with surrounding materials. Rocks come from solid minerals. Iron comes from ore deposits. Sand comes from silica. Water comes from the hydrologic cycle. But wood, the material humans have used since prehistoric times to build houses, boats, tools, comes from air. A log floating down a river is a carbon pillar, the tree pulled from the sky. A wooden bridge is a block of condensed air. A wooden guitar sings thanks to the vibration of old air. When you burn firewood, the flame that bursts up is solar energy, the tree stored decades ago. When you warm yourself by the fire, you're feeling ancient light returning to the world. I want you to notice this. When you burn wood, the smoke rising is CO5 returning to the air. The cycle completes. Carbon flies back where it once belonged. Light returns to its original form. Photons as heat. When you understand that 99% of a tree's mass comes from the atmosphere, you'll look at forests with different eyes. Forests aren't just trees. Forests are carbon vaults. Forests are atmosphere regulators. Forests are the planet's light record. A 500-year-old ancient tree isn't just a living thing. It's a 500-year storage of CO5, 500 years of light, 500 years of energy, fixed by cellulose and lignin. Trees aren't matter growing from soil. Trees are organized air, and that organization, the electromagnetic arrangement of carbon taken from the air, allows this object to stand tens of meters tall, bear enormous loads, and become home to entire ecosystems. Once you've digested the truth that a tree is almost entirely made from air, you'll soon realize something even more profound. Carbon doesn't stop at the tree. It continues its journey, and eventually it becomes you. The carbon in an oak trunk can become the carbon in a squirrel, then in a fox, then in the soil, then back into a tree, then into the fruit of that tree, then eaten by a human. Carbon moves through the world like a versatile actor, constantly changing roles, but never leaving the stage. That's the carbon cycle, and it explains a beautiful truth. All life on Earth is connected through the same carbon atoms, reused billions of times. Imagine a CO5 molecule that a tree just pulled in through its stomata. Its carbon is grabbed by rubisco, forced into a reaction by ATP, turned into glucose, then into cellulose. That carbon becomes a wood cell, then part of the tree trunk. A deer comes and eats those leaves. Carbon changes roles again. Now the carbon becomes part of the deer's muscle. A wolf eats the deer. Carbon changes roles again. It becomes bone, blood, fur. When the wolf dies, bacteria decompose it, and the carbon returns to the soil and air, and the tree pulls that carbon back into a new cycle. Every carbon atom you carry in your body, in your bones, in your DNA, in your brain, in your heart, has once been part of countless organisms before you. Some carbon atoms in you were once in dinosaurs, in thousand-year-old ancient trees, in giant whales, in a farmer 2,000 years ago. And the entire journey began where? In the air. You can open your refrigerator and see meat, eggs, milk, vegetables, fruit. But if you strip away all the complicated biological descriptions and look with a physical eye, you see only one thing. It's all carbon rearranged in different ways. The carbon in beef didn't come from soil. It came from grass. The carbon in grass came from CO5. So beef in the physical sense is air rearranged in the style of a cow. The carbon in a carrot came from CO5. The carbon in bread came from CO5. The carbon in the piece of paper you're holding came from CO5. The carbon in a lump of coal is ancient CO5, compressed over millions of years. The carbon in this page, on the table you place it on, in the wooden roof over your head, all of it is carbon that once floated in the air. If you could look at the world through carbon vision glasses, you'd see everything alive, glowing with the same color, the color of recycled carbon. Carbon is neither created nor destroyed. It just changes roles. The carbon cycle isn't a straight line. It's a loop. Air tree animal, soil air tree, and so on, for hundreds of millions of years. When you breathe out, you exhale CO5. But that CO5 isn't meaningless waste. It's the life source for trees. The carbon you exhale could become part of a leaf in the park near your house a few months later. Then that carbon could become part of an apple someone eats. Then that carbon could enter the body of a child somewhere else. Carbon has no home. It just keeps passing through different life forms. This is one of the truths that makes me love physics more than ever. You are not an independent entity. You are a temporary configuration of carbon, hydrogen, oxygen, atoms borrowed from the world. You only hold these atoms for a few decades. Then they continue their journey. The carbon in your hair will become part of the soil. The carbon in your blood will become CO5 in the atmosphere. The carbon in your bones could become mineral in a limestone rock. No carbon molecule belongs to you, but in this moment, they temporarily assemble into you. That feeling really changes how you see yourself. You are not separate from nature. You are a temporary version of carbon that nature is experimenting with. When you eat an apple, you're eating light and air that the tree has reorganized. When you eat chicken, you're eating light and air that the tree turned into seeds. Then the chicken ate. Then you ate the chicken. What moves from one thing to another isn't life substance, but carbon. The same carbon that trees pull from the atmosphere. That leads to a humbling and poetic truth. You are air that a tree once processed through a series of complex chemical reactions. If trees didn't fix carbon, animals wouldn't exist. If animals didn't eat trees, or eat other animals that ate trees, carbon wouldn't spread through the ecosystem. Every form of life depends on the same raw material, carbon falling from the sky as CO5. Look at any field, any forest. That's billions upon billions of carbon atoms, slowly moving through generations of organisms. Trees absorb carbon. Animals eat trees. Other animals eat animals. Bacteria return carbon to soil and air. No carbon atom is added or lost. The carbon cycle is Earth's most perfect recycling system. And you, whether you like it or not, are part of that flow. Your carbon will continue somewhere after you leave this planet. It will go into trees, into animals, or back to the sky. Carbon doesn't end. It just changes roles. If carbon can change roles from tree to animal, then from animal to soil, then back to tree, then you already know what comes next. The carbon in your body was also once air, not in a poetic sense, not in a philosophical sense, but in the strict chemical, physical, molecular sense. Every carbon atom in you, every carbon in your hair, skin, bones, muscles, every carbon in the DNA molecules, storing information about you, all of them once existed as CO4, floating in the atmosphere. And that means you are air arranged differently. You are not separate from nature. You are not outside the carbon cycle. You are part of it. The carbon you carry is just carbon that trees temporarily fixed. Trees take CO4 of the air, turn it into glucose, then turn glucose into cellulose, starch, lipids, proteins. Animals eat the trees. Then another animal eats that animal. Then you, a higher creature who seems to create yourself, are actually just a special molecular configuration of the same carbon atoms that trees pulled in through stomata. If you eat meat, your carbon was once the carbon of the grass the cow ate. If you eat fish, your carbon was once the carbon of ocean algae. If you eat bread, the carbon you just ate was once atmospheric carbon. No exceptions. Not a single carbon molecule in you appeared from nothing. You only borrow carbon from plants. And one day you will return that carbon to the air, just like every organism that ever lived before you. This may sound scary to some people, but for me it's one of the most beautiful truths of science. There is no real boundary between you and the world. Carbon doesn't arrive and stay forever. It isn't loyal to any creature. You don't own the carbon in you. You only hold it temporarily for a few decades. Carbon moves freely through time and space, but at some moment in the universe, it chooses to stand in the shape of you. That's why I always say that the physical view of the human body doesn't make the world less beautiful. It makes it more beautiful. Try to imagine this. A carbon atom in your brain cell. The atom that lets you think, remember, love, dream, could have once been in the leaf of a maple tree 80 years ago. Before that, it was part of atmospheric CO4. Before that, maybe it was in a forest bird, in a pine trunk, or in an ancient sea creature thousands of years earlier. The journey of carbon never ends. It just changes form. Carbon isn't lost. It's only reorganized. And in this moment, it's organized into the structure you call me. The question, what am I, if answered with physics, is very different from what you're used to hearing. You are not solid, liquid, or gas. You are a wave of organization, a temporary stream of electrons and protons arranged in a special shape, a shape that allows you to think, laugh, cry, love, worry, create. But the material that forms that shape, it's air restructured in a special way. Look at your hand. The carbon in it once floated in the air. Look at the wooden wall next to you. The carbon in it also once floated in the air. The only difference is the arrangement. Same atoms, different structure. A tree and a human use the same kind of atoms. But the result is two completely different worlds. That's the beauty of physics. Same alphabet, countless ways to write. Carbon is the alphabet of life. Each species is a book written in the language of carbon. And you, yes, you are also a book of carbon, temporarily written, then rewritten, then rewritten, then rewritten again, through countless generations of organisms. This also gives an interesting perspective on your relationship with the air. Most people think air is just something you breathe in, shapeless, without significant weight, not real in the material sense. But your body proves the opposite. If air had no weight, your body wouldn't either. The carbon in you, about 18% of your body mass, was once invisible gas. That always makes me want to smile when I hear someone say everything truly real is heavy and solid. No, the heavy and solid things are precisely the things that were once light and invisible. That's how nature plays. Take things you can't see and turn them into things you can touch. That's why every time I look in the mirror, I see something almost humorous. I am a very well-organized cloud of CO. Your hair was once gas. Your skin was once gas. Your brain was once gas. Your heart was once gas. And if that doesn't amaze you yet, remember this too. The carbon in you is billions of years old. Carbon atoms don't age. They just change homes. The carbon in you has been here since Earth was a molten hell. It witnessed dinosaurs, receding seas, melting ice, mountains rising and collapsing. Your carbon is one of the oldest witnesses in the universe, and it will continue its journey long after you leave the stage. So when you say, "I am me," physics replies, you are carbon in a temporary configuration, nourished by light. That may make you feel small, but for me, it makes humans more beautiful, because it reminds us that you weren't born separate from nature. You are nature in the form of consciousness. And once you've seen that you too are made from air, once you realize the carbon in you, in trees, in every organism, is just different roles of the same ancient atom, then perhaps you're also approaching one of the conclusions I always try to tell my students. Nature doesn't become less beautiful when you understand it. It becomes more beautiful. There's a story people often repeat, that science ruins beauty, that analyzing too deeply strips the world of its mystery. I always find that argument strange. It's like saying that if you know how a piece of music is written, you can no longer hear the melody. Or if you know colors come from light wavelengths, the sky becomes less blue. Or if you know how flowers are pollinated, they become less beautiful. No, that's not true at all. The truth is this: the more you understand, the more wondrous the world becomes. Not because you add magic to it, but because you start seeing the magic that was already there in nature's structure. Remember the tree we've traveled with through all these sections. When you were little, you thought trees grew from soil. When you grew older, you thought trees absorb water, absorb nutrients, and then grow. That seemed reasonable, simple, easy to accept. But when you truly understand it, when you know the tree isn't made from soil, but from air, when you know every carbon molecule in the trunk once floated invisibly around you, when you know a leaf is a quantum machine harvesting photons, when you know light from a star 150 million kilometers away gets trapped in chemical bonds and becomes wood, when you know cellulose is a polymer of sugar and lignin is molecular cement, when you know the trunk is a record of the sun's energy, then you look at the tree in a completely different way. It doesn't become less beautiful. It becomes thousands of times more beautiful. Before, you only saw the shell. Now you see the inner structure. You see the movement of electrons, the journey of photons, the arrangement of electromagnetic fields, the cycling of carbon. You don't just see a tree. You see the physical design of life. I remember standing in front of a tree for a very long time, doing nothing, just looking, and the feeling wasn't, "Ah, I understand it all now." No more mystery. It was, "I can't believe all of this is really happening." I could imagine every photon landing on the leaves, every electron jumping energy levels, every CO4 molecule being split, every cellulose chain growing by one more glucose unit, every wood ring thickening by a millimeter. And because I know that, the tree is no longer just an inanimate block of matter. It's a wondrous machine that nature took hundreds of millions of years to optimize. Science doesn't kill beauty. It unlocks beauty. It opens the door for you to step inside. This is what I always want to say to people who claim science makes everything unpoetic. Poetry doesn't lie in vagueness. Poetry lies in truth. The fact that trees absorb light and fix carbon, the fact that you are made from air, the fact that electrons build the world, the fact that the universe is structured by laws, the fact that nature needs no added magic because it is already magic. What makes the world flat and dull isn't science, but habit. We look at trees too often and forget how extraordinary they are. We breathe too regularly and don't notice that our lungs are exchanging carbon with trees. We eat fruit without remembering its atmospheric carbon repackaged. We live in wooden houses without realizing we're living inside solidified light. But science pulls you out of the inertia of familiarity. It demands you look at the world with fresh eyes, with primal curiosity. It forces you to be amazed again, amazed in a deeper, more rooted way. A tree becomes more beautiful, not because it's just a tree, but because you know how beautiful the world inside it is. You don't have to believe a tree has a soul to see its wonder. You just need to know how photons and electrons work to fall into a state of awe. Science doesn't replace emotion. It amplifies emotion. It gives you more language to describe beauty, more depth to experience beauty, more imaginative space to see beauty larger than you ever thought. And the more you know, the more the world opens up. A leaf is no longer just a leaf. It's a small-scale energy factory. A drop of water is no longer just a drop. It's oscillating hydrogen bonds. A rock is no longer just a rock. It's a mineral crystal lattice trying to hold a stable structure. A gust of wind is no longer just wind. It's moving atmospheric pressure, and that pressure is the weight of tons of air above you. Truth doesn't make you smaller. It makes you bigger. It makes you freer in how you see the world. And the beauty of science isn't in answering every question, but in creating new questions, new perspectives, new layers of meaning. When you understand nature, you no longer stand outside, admiring it like a static painting. You step inside and become part of it. You see the web connecting trees, light, carbon, you, the whole planet, and you realize we don't live in the universe. We are the universe knowing itself. When you know the carbon in trees comes from air, when you know light is frozen into wood, when you know every molecule in the trunk is the result of electrons, photons, enzymes, and electromagnetic fields. Try doing one simple thing. Look at a tree again, but with new eyes. I want you to really try, not in your head, not with imagination, but with real eyes. Stand up, go outside, or look out the window. Find a tree, any tree, big tree, small tree, a tree you've walked past 1,000 times without noticing. Now look at it for a few seconds. Don't look at it as a tree. Look at it as the materialization of the sky. Look at it as the place where air has been gathered into solid form. Look at it as the place where light has been imprisoned in chemical bonds. Look at it as a silent quantum machine at work. Look at it as a record of light over many years, many decades. If you look closely at the trunk, you'll see the layers of wood, the growth rings, the cracks and grain patterns. All of it is the language of carbon. All of it is the story that light tells through matter. When the leaves sway lightly in the wind, you're seeing the result of billions of chemical reactions that happened in every cell. When sunlight filters through the canopy, you're seeing photons for the last time before they're absorbed and become chemical energy. When you see the tree casting its shadow on the ground, you're seeing the physical shape of the electromagnetic bonds that carbon chose to stabilize energy. I want you to reimagine the journey of any random carbon atom in the tree you're looking at. Maybe 10 years ago, it floated hundreds of meters up as CO4. Maybe 100 years ago, it was in a forest bird. Maybe 500 years ago, it was part of a rotting ancient trunk. Maybe 50 million years ago, it was in the atmosphere of the dinosaur era. And today it stands in front of you as solid wood. The tree you're looking at isn't a stationary object. It's the present moment of a carbon flow stretching millions of years. You're only seeing one frame of an endless movie. Now look at the canopy. Each leaf is a photosynthesis engine. Each engine contains thousands of chloroplasts. Each chloroplast contains millions of chlorophyll molecules. And each chlorophyll is a photon antenna waiting for light. It's not any supernatural magic, just physics operating exactly as it must. Air enters through stomata. Photons strike electrons. Electrons run through the transport chain. ATP is born. CO4 is split. Glucose is formed. Glucose links into cellulose. Cellulose is filled by lignin, and you have wood. When you look at the tree with that knowledge, you no longer see it as an object. You see it as a physical phenomenon happening right in front of you. Just like when you look at a rainbow and know it's scattered light, it doesn't make the rainbow less beautiful. It makes the rainbow more profound. Understanding the tree doesn't make the tree less mysterious. It makes you see the mystery in the right place. The trunk is the result of electromagnetic interactions you can't see. The leaves are the stage for quantum reactions the human eye can never observe. Wood is a temporary fossil of sunlight, and the carbon in you, yes, you too, is interlaced into that story. Look at the tree one more time. Step back a little. Imagine the atmosphere that once surrounded everything has been gathered into that shape. Imagine light traveled 150 million kilometers just to become part of those wood rings. Imagine you're looking at an object built from gas and light. When you see that, your relationship with nature will change. You won't walk past a tree without noticing anymore. You won't think trees are simple anymore. You'll see a living physical story. And the most wondrous thing is, you too belong to that story. When you look back at the tree with those new eyes, you might also start to see one more thing, something physics always whispers to anyone willing to listen. You and the tree aren't as different as you think. We look at trees as something other species, standing still, green, silent, not running. But if you peel away the biological layer and look deeper into the operating mechanisms, you'll see both you and the tree are telling the same physical story, just playing different roles. The tree uses light to build carbon. You burn carbon to live. The tree takes photons, excites electrons to higher energy levels, stores that energy in the chemical bonds of glucose, then builds cellulose, lignin, wood tissue. You eat the tree, or eat animals that ate the tree, break the carbon, hydrogen bonds in glucose, release the sunlight energy the tree had stored, and use that energy to run, breathe, think, love, worry, work, live. The same energy, the same carbon, just running in opposite directions. The tree builds the world from the bottom up, from photons to chemical bonds to solid matter. You break the world from the top down, from solid matter to chemical bonds to photons and heat. This truth makes me smile every time I think about it. You're operating in the reverse direction of the tree, yet still using the exact same physical laws the tree uses. When you go for a run, the ATP in your muscles is broken down, releasing energy the tree once stored in glucose. When you light a campfire with tree branches, the flame bursts not from wood fuel, but from released solar photons. When you exhale CO hive, you return carbon to the sky, so the tree can pull it back in and start the loop again. There's no war between you and the tree, just the flow of carbon and energy passing through both. Nature doesn't classify plants and animals as two separate worlds. That's how humans label things. Physics doesn't care. Physics only sees the flow of energy and matter. And in physics' eyes, you and the tree are using the same set of rules, the same kind of electrons, the same kind of bonds, the same kind of electromagnetic fields. You are carbon temporarily arranged in the Homo sapiens style. The tree is carbon temporarily arranged in the photosynthesis style. But both are different versions of the same mechanism. Light, electron, chemical bond, matter, life. When you understand this, you start to see nature not as divided compartments, but as one unified network. The tree needs the CO fate. You exhale. You need the O fate. The tree releases. The tree stores photons. You release photons. The tree holds carbon. You return carbon to the atmosphere. The tree stands still, but turns air into matter. You move, but turn matter into energy. Two processes, two directions, but the same equation. This leads to a very beautiful conclusion. The unity of nature is not a philosophical idea. It's a physical fact. When you touch the tree trunk, you're not touching a plant. You're touching carbon that was once CO fate, once light, and the same kind of atoms that make up you. When you look at the leaves, you're not looking at a different object. You're looking at another version of the physical process happening in your own cells, just with a different purpose. The tree lives by building the world. You live by decoding the world. But the underlying physics is identical. I've always thought that if people truly felt this truth, we would stop separating ourselves from nature. You don't have to stand outside to protect trees. You're part of the cycle. The tree is also in. You don't live on Earth. You are Earth. You are atmospheric carbon, temporarily organized into a thinking structure. And the tree, in the deepest sense, is also you, just arranged differently, in electrons. And now, after peeling through all these layers, from leaf to photon, from CO fate to cellulose, from electron to wood, from tree carbon to the carbon in you, I want to return to something very small, very ordinary, where it all began, with one silly question. Where does a tree get its mass from? It sounds like a 9-year-old's question, a question adults usually laugh off, thinking it's obvious. From the soil, of course. But as I've said, the simplest questions often lead to the deepest truths. And this silly question has led you, and all of human science, to a picture so beautiful, it's almost unbelievable. The tree doesn't grow from soil. It grows from air. Not water, not minerals, not magic, but from sky carbon and the energy of a star. You started with wrong intuition. Roots suck up soil. You corrected it. So the tree must be made of water. Wrong again. You tried from minerals. No. And finally, only when you dared to keep asking, when you didn't settle for easy answers, did you reach the truth. The tree is air rearranged by light. Even more beautiful is that this truth doesn't stop at the tree. It spreads to all of life. It says carbon moves like an actor in nature's gigantic play, sometimes as a leaf, sometimes as a deer, sometimes as me, as you, then back to the sky. It says you and the tree aren't two separate worlds. You're just two different ways. The universe organizes the same material. It says solid matter, the thing you think is most real, is just electrons, locked in a temporary electromagnetic configuration. And it says light, the thing you thought was only for seeing, is the cement of life, the foundational energy that turns air into matter. All this beauty began with one small question that many people think is stupid. That's why I always tell my students, and now you don't be afraid of stupid questions. The scariest thing is not daring to ask, because every time you ask why, the universe reveals one more secret, and the more you ask, the bigger the world becomes than you ever imagined. If you think the gift of science is answers, you're wrong. The real gift is the ability to look at the world with curious, undefended eyes, without shame at not knowing. Science doesn't take away nature's wonder. It teaches you how to see the wonder where you once thought things were ordinary. And if a tree, something you've seen your whole life, can hide stories this beautiful, imagine how many other things out there are waiting for you to ask the right question. So I'll end with what I truly believe. You're not bored with the world. You just haven't asked enough questions. And the world, when you look at it with curious eyes, is always more beautiful than you think. Thank you for joining me on this journey from soil, water, minerals, air, light, carbon you. And if you want to keep exploring how the universe really works, just keep that why question in your pocket. It's the most powerful tool you have. If you enjoyed this journey of discovery, please subscribe to the channel so you don't miss the next magical physics stories. See you again on the next adventure with the universe.